tennis ball is our proton. The tubes, the metal cylinders that guide the proton, and the cocktail sticks, the wires that connect the alternating positive and negative cylinders. Dropping the ball through these tubes represents how the proton is attracted to the first negative cylinder. I use gravity to emulate the acceleration the proton undergoes through this attraction. As soon as the proton leaves the first tube, the second becomes negative in order to attract the proton and accelerate it. The first also becomes positive in order to repel the proton. When the proton is within the cylinders, no acceleration occurs, as it has an equal force pulling it in every direction. This means that the cylinders need to increase in length to allow the proton to stay within them for the same amount of time, as it is speeding up more between each cylinder, and the voltages are all changed at the same time. These voltages are very high, causing the final kinetic energy of the proton to be very big. This is another particle accelerator called the cyclotron. It uses magnetic force to create a B field, causing circular motion. Magnetic force is equal to the magnetic field strength, or flux density, multiplied by the velocity, times by the charge of the particle. This is also equal to the centripetal force, as it causes circular motion by being at a right angle to the electric field. Calculated by the mass times the velocity squared divided by the radius. Here are the d's that the proton moves within. It is first attracted to the negative d, and due to the perpendicular magnetic field, it circles back towards the central E field, which then accelerates it towards the other d, which is now negative. Much like the Linux cylinders, they alternate in voltage to accelerate the proton more as it circles. When it exits the d's, it will enter a detector, perhaps like the Geiger-Miller tube. The Geiger-Miller tube is a detector. The proton, represented by the pink ball, enters the tube, which this is a cross-section of. It then interacts with the gas molecules, the green balls, and rips their electrons from them. They are then attracted to the positive central cylinder, but as they do, the electrons rip electrons from other particles, creating an avalanche, which falls towards the centre. This is a representation of a cloud chamber. This ball, soaked in glue, represents the particles given off by a radioactive source into supercooled ethanol vapour and air. The radioactive particles ionize the gas molecules. The ethanol vapour then condenses onto these ions, causing a visible path in the chamber, seen here by how the glitter is attracted to the paths that the glue makes on the paper. This detector displays the randomness of radioactive emissions. This pan represents a bubble chamber. Much like the cloud chamber, the supercooled liquid hydrogen is held at its boiling point, as is the water in my pan. The ions that are created by the radioactive particles, represented by this metal stick, hit the atoms, allowing the liquid hydrogen to boil, creating lines of bubbles in its path. This also displays the random nature of radioactive emissions.